right, in this video, we are talking about Lewis acids and bases. First, let's just draw a alcohol, and we're going to react it with an amine. And this is going to be really reminiscent of our Bronsted-Lowry acids and bases. We're going to try to figure out which side of this reaction is favored. Let's draw in our arrows here. The way that I have it drawn, we're going to use our alcohol as our acid, and we're going to use our amine as our base. We're going to take the lone pair of the nitrogen and pick up a proton. Our second arrow will move the electrons between the hydrogen and oxygen to our oxygen. Let's draw what we have here. Remember, our arrows tell us what happened in the reaction. So if arrows weren't drawn to an atom, nothing changed there. So we still have our oxygen here. We started with two lone pairs, and you can draw them in. And then we gained another lone pair, right? Then our amine, those didn't change. It still has that hydrogen, but it picked up a hydrogen, right? And it lost electrons. Now, this is our Bronsted-Lowry acid base definition of this proton donor. The acid is a proton donor. The base is a proton acceptor. Now, when we decide which side of this reaction it's favored, this is where we use our pKa's. pKa's are really only talking about how good something is at giving up a proton. So when we look at our alcohol, we know the pKa here is around 15. And when we look on the right side, our acid is the protonated amine. Here's our acid, and here's our base. And our protonated amine has a pK of around 10. Now, which side of the reaction is favored is always the weakest acid. So in this case, our reaction is favored to the left. Our alcohol is a weaker acid, and so this reaction is reversible. The pK difference is only around 5, but it's favored on the left side. So this is describing a Bronsted-Lowry acid and base, but let's talk now about Lewis acids. Lewis acids and bases talk about electrons. It's just the terminology we're going to use. A Lewis acid is one that is an electron pair acceptor. Let's look at our mechanism here. The alcohol in this second arrow, here's our first arrow, in the second arrow, look, it's gaining electrons. It is accepting a pair of electrons. And you can see this in the lone pair here on the right side. There's that pair of electrons we gained. A Lewis acid base is one that is donating a pair of electrons. And this nitrogen here is donating that lone pair. See that in the arrow? It's donating an electron pair. So these can be also described as Lewis acids and bases. We use Bronsted-Lowry acid base because it's more specific. It's more specific. So if I were to kind of put a landscape or draw a landscape around acids and bases, this large circle would be Lewis acids and bases that can be used to describe all of them. And then Bronsted-Lowry acids bases are specific because they're dealing only with, they have to be giving up a proton, essentially, if it's a Bronsted acid. Okay, so this terminology is letting us know that, oh, everything is a Lewis acid and base. But we like to describe them more specifically as proton donors, and that's where we start using our pKa's. Let's talk about some specific Lewis acids that you'll be using. Lewis acids are compounds that have atoms with an incomplete octet. These are ones that we use in synthesis. This is more commonly used. Now, these do not have any protons to give. So these are Lewis acids, but are not Bronsted acids. This boron here only has 6 electrons, and this aluminum only has 6 electrons. So these are atoms with an incomplete octet. Carbocations are also Lewis acids. This carbon here only has 6 electrons in its octet. Another example here is that carbonyls are technically also Lewis acids. And you're like, wait a second, each carbon of these have a full octet. Well, this is where resonance comes in. I can draw a resonance structure where I have a carbocation here. So, carbonyls are also Lewis acids. Okay, very weak, but they are also Lewis acids, and that's because they have this resonance form that's showing that that carbon also can have less than an octet here. Let's go through a few other examples of some Lewis acids. So some other Lewis acids that you might see in your career as an organic chemist. Titanium tetrachloride, PlCl3, SoCl2, thionyl-chloride. This thing, oh my goodness, it smells and it will burn your nostrils. Iron trichloride, iron tribromide. These are ones that you'll definitely use in Chem 345. So these are some other Lewis acids to just be aware of. What I want to do is do a reaction with you with a Lewis acid. Now, I just said carbonyls can be Lewis acids, but here I have a stronger Lewis acid present. So in this case, this is going to be our Lewis acid, this aluminum trichloride. This is going to be our Lewis base. Remember that Lewis acids accept electrons. So let's draw our arrows in. Here's our lone pairs here on our oxygen. And what's going to happen is it's going to make a complex, and the aluminum will accept these electrons. So this aluminum has 3 chlorines on it. And there we go. We have our Lewis acid base pair. Lewis acid base pair. Now, this is going to be used in chemistry you're going to be working on in Chem 345. I wanted to make you aware of how these Lewis acids can be used. All right, so this is one way that they can be used. And essentially what you're doing is you're activating this carbonyl. Again, that's Chem 345. Let's now go to another example. Let's go back to this idea that, what about carbonyls? They can act as Lewis acids. Let's do another reaction together. And here I have a carbonyl, and it's actually going to act as our Lewis acid. We have a cyanide anion here. This carbon is actually going to attack the carbon of the carbonyl, and the electrons are going to move up to our oxygen. Now notice here the Lewis acid has accepted electrons. And our cyanide here is our Lewis base. It has donated an electron pair. Now this reaction is actually favored on the left side, and we'll talk about why. But here we can draw in our lone pairs. Then we have this nitrile that's bound. Now I'm not showing the other hydrogen. Now you can here, or you could have left it how it was. We'll talk more about this wedge dash on this compound here in our next videos. Now, what I want us to focus on is how we can determine this reaction arrow. So when we look at Lewis acids and bases, they typically are not giving up a proton. However, pKa's can be used to describe whether or not a reaction is possible or could happen. And the way we want to do this is we want to look at the conjugate pKa, the pKa of its acid. So let's draw this here. So if we were to look at this nitrile or this cyanide anion. This is a base, and this is its conjugate acid. HCN is a weak acid, and its pK is around 10. All right, and let's look over here. Here's our product. Now, the conjugate acid of this, if we add a proton to it, so we're adding a proton to figure out the conjugate acid. Okay, the conjugate acid of this alkoxide would be an alcohol. All right, well, we know the pK of an alcohol is around 15. When you're looking at the conjugate acids, the lowest conjugate acid, the side with the lowest pK of the conjugate acid is favored. Now, this is opposite of what we've just talked about, Bronsted-Lowry acids and bases. And the way to remember this is that if I have a conjugate acid, let's see, this one's pK of 10 and this alcohol's pK of 15. When I compare just these two, it looks to me like this HCN is more likely to lose its hydrogen, meaning that this CN minus is more stable, right? This is more stable if I just compare it to this guy. So this would be less stable. That pKa is telling us that that anion is less stable, okay? Less likely to give up its hydrogen than HCN, which has a pK of 10. So when you do Lewis acid-base reactions, you can use the conjugate acid pKa if there is a proton that is available. This is going to be useful as we start to do more reactions, and I might bring this up again, which is why I'm bringing it up now. So in this case, because the pKa of its conjugate acid is lower, that means that this side is favored. Again, looking at the stability of the anion, essentially. Let's review again why I even chose this as a Lewis acid. Well, remember that our carbonyls can undergo resonance. So when it interacts with this is called a nucleophile, but also here it's a Lewis base. It has a pair of electrons that it's cool with giving up. It's going to donate an electron pair, and that is how we know that the reaction can occur. I want to make a really important note here, though. The way that I have my arrows drawn is it's on this top structure, okay? Now I'm drawing an arrow here, a mechanism going to a resonance structure. When we draw mechanisms using curved arrows, we always want to use the major resonance structure. Oops. Major, there we go, resonance structure. If I look at these two resonance structures I have on the bottom left, this is our major. Octet rule is one of the top rules for resonance. Got to fulfill the octet rule. This carbon does not have a full octet. That's why it can act as a Lewis acid. So this is our major resonance structure, and we always like to draw mechanisms using major resonance structures. So draw mechanisms using major resonance structures. I show you this on the bottom to show you why this carbonyl can react in the way that I've shown it. There's one other topic I want to go over, which is amino acids. And so let's just draw a generic amino acid. We're going to jump back to our Bronsted acid-Lowry base reactions here. So I'm just going to draw glycine. Now, on glycine, we have two different sets of protons. okay? That could potentially be acidic, right? We have our carboxylic acid here. This pK of a carboxylic acid is typically around 5. But because of inductive effect, this nitrogen is withdrawing electron density. The pKa of glycine for this carboxylic acid is around 2.3. Okay. What happens with amino acids is that they tend to, when they're just present with themselves, is that the acid will actually donate a proton to the amine. And so what you'll end up getting is a protonated amine. The pKa of this protonated amine, if you guessed it already, that's right. The pK is around 10. It's around 9.6. When we're looking at these two structures, which side would be favored? Well, we know we want the weakest acid favored, right? So let's figure out what arrow to draw here in this box. We want the weakest acid to be favored, and that would be the right side. pKa of 9.6. Now, the difference here is a little more than 6, so it's definitely going to be favored on the right side. But it's still reversible. There's a terminology we use for compounds that exist with an anion as well as a positive charge, and this is a Zwitterion. I'm giving you this term so you can sound really cool when you go and hang out with your friends and talk about Zwitterions. So this is glycine. And I wanted to make you aware that amino acids exist as a Zwitterion. This is the major form of amino acids, and that's because we have this acid that's in the presence of a base. Now, this doesn't happen intramolecularly. This is like one glycine sees another molecule of glycine. That's where the proton transfers happen. However, I wanted to make you aware that these exist as Zwitterions. Okay, again, using our principles of Bronsted-Lowry acid-base reactions. So that's it. So in this video, we went over Lewis acids as well as Bronsted-Lowry acid bases. And I just wanted to highlight something on our Canvas page. I just posted a practice exam for you. Now, this exam is going to cover material up until the end of this video. Here's a practice exam, and I want you to work on it on Piazza. So as you start to work on it, post your answers on Piazza. I'll post the questions on there as well. This is really going to be reminiscent. I just made it last night actually for you. So this is going to be really similar to the exam we're going to have next Thursday. I think there's 8 pages here. And you'll find that it talks about resonance and acid and base and drawing chairs and Newman projections and isomers, constitutional isomers, all of that fun stuff. These are the foundations for all of your organic chemistry knowledge. Oh, there's an orbital question. Yep, molecular orbital theory is fair game. So give that a go. And as you come up with questions, make sure you write it on Piazza so that way myself and your TAs can help. And it's really fun to get all the class kind of involved. Some of your classmates are going to learn from questions that you post, and it's really fun when we can all kind of learn together. Also, did you sign up for peer learning? There's probably some sections left. Let's see. Oh, no, I'm not interested. Let's go here. Hey, look at you. Look at you guys. Look at you, Alyssa, Will, McKenna, Clara, Risma, Destiny. Sweet. Thursday, there's lots of time. So yeah, there's still some spaces there on peer learning, which is a really great way to meet up with your classmates. And I think that's it. Oh, also one more note. Sorry. Alternate exam time. If you haven't gotten an email from me, that's because I messed up the form and I thought it was going to collect your emails and it didn't. So I really apologize. Make sure you go, if you haven't gotten an email from me, and you submitted an alternate exam time, please go back and resubmit. I need your email as well. So I messed up on that and I was trying to guess who contacted me. So please contact me again through this form if you have something else that is inhibiting you from coming to our exam on Thursday, and I will adjust your time. I think that's it for this video, and I will see you in the next video.